Hey guys, welcome to Module 5.2. In this module, we're going to be talking about bivariate statistics, which are statistics where we analyze two variables and we try to tease out the relationship between them. I'm going to start by talking through the meaning of statistical significance, and then I'll go through the different tests that we can use to conduct bivariate analysis. Let me briefly mention before I do that your practice assignment for this week is due Sunday like always and is focused on the semester research project. And then next week's practice assignment is a problem set. And that problem set will have questions about bivariate analysis, which we're doing this week, as well as multivariate analysis, which we're doing next week. So I'm going to post it in the next couple of days. If you want to practice the bivariate analysis stuff while it's fresh, you might want to consider doing the first half problem of the problems from next week's practice assignment this week. So this week you work on the semester project for your group project, this week you work on the semester project for your homework assignment. Next week is a problem set, and that problem set contains some of what we're doing this week in the mini lectures and the chapter. And so you might want to do both your practice assignment for this week, which is related to the research project, and the first half of your practice assignment for next week, which is the stuff we're learning in the reading and the mini lectures for the week. You don't have to, I'm just giving you the heads up. All right, one other thing to note before we get started is that I'm going to spend most of my time in this module on the major concepts of bivariate analysis and not on the formulas or the math underlying how and why we do the things that we do. My focus is on getting you what you need to actually conduct these analyses and to understand what you're doing. If you want to know more about how we get there or why it works, if you really want to be able to stretch your wings on this stuff, then you want to take a statistics course, either in this department or somewhere else, and I'll always be happy to talk to you about that stuff if you want some recommendations or ideas. Okay. When we look at the relationship between two variables and we say that relationship is statistically significant, what we're really saying is that the two things are related and that we're fairly certain that that relationship is real and not just due to chance or randomness or luck or anything else. Understanding statistical significance starts with understanding inferential statistics. And the idea behind inferential statistics is that we're looking at patterns and we're looking at relationships in sample data, and then we are inferring information about the population from which that sample is drawn. So for example, if we take a poll of 5,000 UNT students and then we infer information about the full student body, that's inferential statistics. Inferential statistics aren't perfect. It's always possible that we see a relationship in the sample that's not actually there or that even wouldn't be possible in the full population. So maybe 5,000 of the students that we poll have 75% College of Music students. And so we then infer that 75% of all UNT students are in the music program. In this case, our sample is biased in favor of music majors, right? Meaning that any random person, any random respondent that we pull has a much higher probability of being a music major than any random student that we pull from the population of students. And what that means is we can't learn anything from it that we could then turn around and apply to the full population of UNT students. So the first thing to note when we're thinking about inferential statistics is that they only work if we have a true random sample. If we have a bias sample, like one of 75% music majors, then we cannot assume or infer that the relationships we see in the sample are also present in the full population. Right. Okay, let's look at statistical significance in a little bit more detail. When we say that the relationship between some X and Y is statistically significant, we're saying that there's a meaningful relationship. In other words, there's not a random connection, and it's not due to chance. I know I'm going to hammer this home until you get it. To determine that, to be able to comment on statistical significance, we look at the strength of the relationship between X and Y. If there is a relationship in the full population, then we will expect to see a relationship in the sample we pull from that population, right? And that observed relationship, the relationship in the sample that tells us there is a significant relationship in the population, that observed relationship gets stronger, it gets easier to see as our sample size gets bigger. The more observations we have in our data, the stronger the relationships that truly exist become. The bigger our N, the larger our number of observations, the easier it is to see significant relationships, and the less likely we are to see relationships that don't actually exist in the full population. My third point now follows from those first two and kind of flips it around a little bit. So if a relationship is statistically significant, we can assume that what we see in the sample will also be true for the population. I've been talking about that as though it's binary, as though a relationship either is statistically significant or it is not. But in reality, that's not how we do it. Instead, we look for levels of significance. We say that something is statistically significant with 90% confidence, or 95% confidence, or 99% confidence. And those are the three conventional levels in political science and in social science that we use. And each of those levels means we are that percent certain that the relationship we see in our sample is also present in the full population. So higher is better, right? 99% confidence is better than 90% confidence. Higher is also harder to find in a sample. To get to 99% significance levels, we need either a really, really strong real-world relationship that shows up even in small samples, or we need a really big sample size. If we've got a lower level of significance, then that's a weaker test of statistical significance. So we're saying that, for example, we're 90% confident that this relationship we see in the sample is also present in the full population. And 90% is pretty good, but it's also wrong 1 in 10 times. I'd certainly rather be 99% sure that a relationship I see in the sample is also present in the full population than I would be 90% certain or confident. Okay, next point is this. When we talk about investigating the relationship between two variables, we use the language of estimating. And that's because we don't have data on our full population of cases, right? We always use a sample. And so we can't ever truly know for a fact what the really true relationship between some X and Y may be. But what we can do is get data on a good random large sample and then calculate the relationship between X and Y in that sample. And then we can say that the relationship in the sample is an estimate of the relationship in the full population. That calculating the relationship, that means calculating the statistical relationship between the two variables. And the statistic we use to do that, and there are many of them, they are collectively called test statistics. They are called that because we are testing the relationship between X and Y to see if it is statistically significant. And all of that is about estimating the relationship in the full population. But we can't really measure the full population. And so there's always some uncertainty. There's always some mismatch between the data we have and the population about which we're drawing inference. And we don't know what's true about the full population about which we are drawing inference. That gap, that distance of uncertainty between what's real or what we think is real and what we've estimated, that's a measure of uncertainty. And we can calculate a measure of uncertainty, and you'll see it with almost every test statistic there is, called the standard error. In more in-depth classes that teach statistics, which again this course doesn't, in those classes the standard error becomes really important from day one. For now, it's important to understand conceptually that we are always uncertain about what we claim to find, and that we want to try to measure that uncertainty and tell people about that uncertainty so that they know how confident we are in our results. Standard errors are a really important way to do that. And standard errors are what we use to calculate confidence intervals. Let's look a little more at the difference between what we measure in our sample and what's true in the full population. So imagine we have a full population of voters where 60% of that population, so 6 out of 10 voters or 60 out of 100 voters, vote Democratic. With me so far? Okay. Now, how likely is it that if we take a poll of 100 voters, between 50 and 70 of them vote Democratic? In other words, how likely is it that our sample proportion, the proportion in our sample, will turn out to be within 10% of the population proportion, the proportion of voting Democratic in the full population? In other words, what is the probability that the sample mean approximates, in this case, is within 10% above or below the population mean? What is the probability that the sample mean gets pretty close to the population mean? To answer that question, we build what is called a confidence interval around our test statistic. I'm going to pick up next time talking about exactly how we set about doing that. So take a break, stretch your legs, get some coffee, get some water, go walk your dog, take a nap, go to sleep, eat some food, go work out, do whatever you do. And I will see you for lecture 2.